We're going. Okay, so 6-5, the second half of 6-5, we're talking about this idea of operations with radicals. We're going to add, we're going to subtract, we're going to multiply, and we're going to divide them. I know, this is all strange. So fourth hour when you're watching this, everybody's smiling and laughing right now. Starting with multiplying radicals. The process of multiplying radicals comes from a property that deals with this. If I have the square root, the square root or the nth root of some number and multiply it by the nth root of another number. Very simply multiplying two similar radicals together. All we do is keep the radical the same root and then multiply the stuff underneath together. That's the basis of multiplying radicals together. Simply multiply, they're called the radicands. That's a fancy math word for the stuff underneath the radical. So as we approach a problem like this, we're simply going to do that. If it's underneath the radical, we multiply it. If it's outside of the radical, we multiply it. Okay, so looking at this, I'm going to go ahead and multiply 6 and 4 together, and that's going to give me 24. I'm going to keep my radical the same and multiply the stuff underneath. 8 times 2, you get 16. Okay. C cubed times c to the first power, you get c to the fourth power. And then d to the fifth times d cubed, you get d to the eighth power. So again, recap, all we simply did, multiply the stuff outside of the radical times the stuff underneath the radical. And remember, add your exponent. All these properties of exponents still apply, and they move forward from there. After you multiply, simplify. So as we look at this, again, look at the index. The index is the important thing. I have the square root, so we're looking for sets of 2 or perfect squares. The nice thing about this, 16 is a perfect square. And so the square root of 16, we get 4. That's from 16. And then we ask ourselves the same question. I want sets of 2. So we say, how many sets of 2 can you get out of 4? The answer is 2. So I would bring a c squared out. Again, this we talked about yesterday as well. I have an even index, an even exponent. Watch out for the odd results. Remember, if there's an odd result, you need to have the absolute value around it. Then again, how many sets of 2 can you get out of 8? Well, I can get 4 of those. So I have d to the 8th power. Okay. And there's nothing left over, which is nice. I'm sorry, not 8, 4. Excuse me, 4. Okay. There's nothing left over, but don't forget I had this 24 on the outside as well, so I have to account for the 24. And then we just multiply the leftovers. So 4 times 24, you get 96. And then you have c squared and d to the 4th power. That would be your final answer. There's no negative exponents. There's no radicals left over. Everything is simplified as it can be. Okay. So with that in mind, okay, those of you in class right now and those of you who are watching this video in 4th hour, I want you to try this one on your own. Okay. Those of you watching the video, pause the video and try it on your own, and then we will go forward and explain it after we're done. Okay, so looking at the problem, as we did before, we have radicals being multiplied, and they're the same index, which is good. So multiply the outside stuff, multiply the inside stuff. So 2 and 3, if we start with those, 2 times 3, you get 6. So the outside starts with that. Keep the radical the same, it's the 4th root, and multiply the inside stuff. 8 times 2, you get 16. X cubed times x to the 5th, you get x to the 8th power. Y squared times y squared, you get y to the 4th. So your first line of offense here is just to multiply similar things together, outsides and insides. After that, we look to simplify, just like we did in the warm-up. We have the 4th root, so we have to break down our numbers now and see what that comes to. So 16, if you use the factor tree, you get 2 and 8, which is 2 and 4, which is 2 and 2. So I can write 16 as 2 to the 4th power now, and I have x to the 8th and y to the 4th, all underneath the radical. Sets of 4, not sets of 2 or 3, sets of 4. So we ask ourselves, how many sets of 4 can I get out of 4? The answer is 1. So I can take a 2 out with nothing left over. So that guy's taken care of. The next one, how many sets of 4 can I get out of 8? Again, be careful. Even root, even exponent. Well, 8 divided by 4, you get 2. That's an even result, so I'm okay there. And then the y's, how many sets of 4 can I get out of 4? Even, 1 is odd, so I need to make sure I put the absolute value around y. We talked about that yesterday, even, odd idea. And I still have that 6 sitting out here. So multiply them together, 6 times 2, you get 12. I have an x squared and then a y in absolute value. Okay. Now, if you came up with 24 out here, it's probably because you considered it a square root as opposed to a 4th root. So you saw I can get 2 sets of 2 out of 4. Remember, pay attention to your index. That tells you the size of the group you want. Okay, so that's the basics of multiplying radicals. The next slide we're going to see is we're going to increase the rigor a little bit and increase what we're talking about as we go. Okay, so now we're going to focus the idea of not multiplying, but adding and subtracting them. We're going to approach this just like you would approach adding polynomials together. And when you have polynomials, you need like terms. So if I wanted to add x's together, I'd have to have just x's. X squareds need to be added with x squareds, x cubed with x cubes, etc., etc., etc. The same thing goes with adding and subtracting radicals. You must have, we call them like radicals. Okay. And what that means, like radicals are nothing more than the same index and the same radicand. Okay, so for example, the square root of 2 and 4 square roots of 2. Those are like radicals because they're both square roots and they're both the square root of 2. Okay. If you had the square root of 5 plus 2 square roots of 3, these are not like radicals. No. Yes. Okay. So when we talk about like radicals, that's what we're looking for. Now, as you go through and do this, at first glance, they might not be like radicals. In our example, that happens. But remember, we always have to look to simplify your radical expressions before you do this. Okay, so jumping into our example here, we're going to do this, but right now, they're not like radicals because it's a square root of 8 and the square root of 50. They're not the same thing. Okay? But if we simplify them down, let's do that. 8 becomes 2 times 4, which is 2 times 2. So really, it's 2 cubed. And since it's a square root, it's an index of 2. So we ask ourselves, how many sets of 2 can you get out of 3? And all third hour would say 1. So I have 4. I can bring out a single 2, but don't forget I have leftovers. Okay, I have a 2 left over. So 4 square roots of 8 really is the same thing as 8 times the square root of 2. That's what that's equivalent to. If we break down 50, we do the same idea. 50 is 2 times 25, and 25 is 5 times 5. So this is 2 times 5 squared. Again, we look for the same idea, sets of 2. I can't take a set of 2 out of 2 because there's none there. There's only 1 there. But I can take 1 5 out because there are 1 2 in a set of 2. So I have a 3 outside. I can bring a 5 out. So those are taken care of. And I have a 2 left over. So the idea here is basically look at each term like its own radical. Simplify each term as its own problem. And then we come back in the end, we add it here. So 3 times 5, you get 15, and you have the square root of 2. Now if I look, I have like radicals. To simplify, all we're going to do is add your coefficients, just like it's a variable. So 8 plus 15, you get 23, and then your radical is unchanged. That's where the mistake is going to happen. Sorry for you in the back, I'll move that up there. Okay. The mistake is going to happen is you're going to want to add the radicand part, and we're not doing that. We're simply add the outsides. The only time the underneath changes is when you multiply or divide. When you add and subtract, it stays the same. Okay? So this is my final answer. Okay? 23 square root of 2. And we're going. Okay, so for conjugates, this idea of a conjugate, it says needed to rationalize the denominator. What we saw so far in the past was something that looks like this. I would have, 3 over the square root of 2. That would be my my problem. And we looked at this the past couple days saying, hey, I have a radical in the denominator. I have to rationalize it so I don't have, this thing pops up like 8 times a day. It's so annoying. So I don't have a radical anymore. And if I look at this one very simply, I could say, well, I have the square root of 2. Well, that's easy because it's the square root. So I would just simply multiply the top and the bottom by the square root of 2 over the square root of 2. Okay. So to rationalize, this would be 3 square roots of 2 over 2. Easy peasy, because I have just a single radical in the denominator. Now, why would I ever leave things easy for you guys? I don't know, but it's because I'm a jerk. So what would happen if I had this? 3 over 2 minus the square root of 3. Okay. Now it becomes an issue. Okay. And I'll show you why. Don't write this part down. I just want to show you why it doesn't work. Okay. You might say, well, I'm going to take the same approach in the top. Hang on a second. Okay, so I had to pause the video for a second to answer the phone, so I don't remember where I was, but just bear with me. If I took the same approach as the other one, again, don't write this down in your notes, just watch. You might say, hey, square root of 2 up here, I multiplied the square root of 2. Down here, I see the square root of 3. Well, if I do that, if I multiply the top and the bottom by the square root of 3, if I take the bottom out, that is 2 minus the square root of 3 times the square root of 3. If I multiply together, what is 2 times the square root of 3? It's 2 square roots of 3. Now, if I do this minus, I get 3. Well, the problem is I still have a radical in my denominator. I haven't changed anything. I still have the same problem. I could go around in circles doing this over and over and over again, multiplying by the square root of 3. I'd end up with the same thing over and over and over again. So what we need to do is use something called a conjugate. Okay? And what a conjugate is, and this is a little side note here, if you have a plus the square root of b, it's got a rational part, a real, and an irrational part. Okay, irrational is the square root part. The conjugate is a minus the square root of b. So if you've noticed what's changed, the only thing that has changed, a is still a. The square root of b is still b. The only thing that changed is the sign in between them. It's the opposite sign. And if you remember in our warm-up, we had like 9x minus 7 and 9x plus 7. Okay, that middle term canceled out. The same thing will happen here when we use the conjugate. So what has changed? Well, I've thrown subtraction into my denominator now. So I need to use a different approach. So when you have subtraction in the denominator, use the conjugate to do it. So if I have this 2 minus the square root of 3, the conjugate of that would be 2 plus the square root of 3. And as before, we have to multiply by something that has a value of 1. So we're going to do this, the same in the top and the bottom. Remember, I don't care if there's a radical in the top. It's the bottom we have to take care of. Okay? So when I multiply these, I'm going to use, just like we had before with x's, I'm going to use a little box to show you what happens. All right, so I'm going to make a little 2 by 2 box out here. So put 2 and a positive square root of 3 on one part, and 2 and a negative square root of 3 in the bottom. And then we would treat it just like we would everything else. We just multiply stuff in. 2 times 2, you get 4. Pretty simple, pretty basic. 2 times the square root of 3 is just that. 2 times the square root of 3. Okay. And the same idea, 2 times the negative square root of 3 is negative 2 square roots of 3. So as you can see, what will happen with those two terms, they're going to cancel out. Because 2 square roots of 3 minus 2 square roots of 3 goes away. And then negative square root of 9. Now, if you remember back to the first half of the class in Algebra 1A, we did this with imaginary numbers as well. Remember, you got I squared and I squared canceled out, so you had a negative 1 there instead. It's kind of the same idea, because the square root of 9 is 3, so this guy actually becomes negative 3. And if I look at what I have in there, if I write this all out, and again, I hope to get to the point where you don't have to write this all out, but so you can see what happens. I have 4. I have a plus 2 square roots of 3. I have a minus 2 square roots of 3. And now I have a minus 3. Okay, because the square root of 9 became 3. And well, if you look in the middle, these guys cancel out. So you have 4 minus 3. So it really is 1. Now, will your denominator always be 1? No. It just happens to work out that way. Okay. So if I rewrite what this has now, the top, I have 3 times 2 plus a square root of 3, and then that's all over 1. Now, that might not always, like I said, it won't always be 1. You might get 6 there. You might get negative 4. Okay. Whatever that combination works, that's what you get. And then to clean things up, we distribute what I had in the top times what I had by the rational. So I have 6 plus 3 square roots of 3. If I had a denominator other than 1, I would put it there. We'll do over 1. And that's what we end up with. Okay, so this is my final answer. So for those in the video, here's one for you. Let's do 4 over 5 minus, or plus this time, the square root of 7. Okay, so if you're watching the video, pause it now and work through it, and then we will have an answer on the other side of the break. Okay, so we approach this problem the same way. We look at our denominator. Okay, I have 5 plus the square root of 7, so my conjugate then becomes 5 minus the square root of 7. And remember, I need to multiply the bottom and the top by the same thing. So we take these guys out. We multiply them out. 5 and the square root of 7. 5 and the negative square root of 7. We go through the same process. 25 here. 5 square roots of 7 here. Negative 5 square roots of 7 here. And negative square root of 49. Okay. Well, again, this guy becomes a negative 7, because that's what the negative square root of 49 is. Okay. If we combine our like terms, I have 25 minus 7. That's 18. And nicely here, these guys go away. They cancel out. No mas. So then what I have left in the top, multiply the tops, so I get 20. And then don't forget 4 times the square root of 7 as well. So 4 times the square root of 7. And all over, the only thing I had in the denominator was 18. So we got to this. Okay. All right. And this last part, as we have a fraction, always look for common factors of our numbers. 24 and 18 all share a common factor of 2. So I can divide all of those by 2. That gives me 10 here minus 2 square roots of 7, and that's all over 9. Okay, so this would be my final answer. Also acceptable if you really felt like writing it this way. You don't have to. 10 over 9 minus 2 square roots of 9, or 2 times the square root of 7 over 9. Both ways are completely acceptable to write your answers in. Okay? In fact, if you got to a problem, if I had 10 plus 3 square roots of 5 over 8, or over 5, let's say. Okay? I could break this up because 10 divided by 5 is 2, and I could do plus 3 square roots of 5 over 5. Okay? So those are a couple different ways to, and we've seen them written like this before. Your quadratic equation typically ended up this way. You have a whole number or a real number and an irrational part. That's what this square root of 5 is, an irrational number. So that's how we broke those parts up. Okay? So this is how we deal with this idea of conjugates. The only thing that changes is the sign in between the numbers. Okay? And really the only thing that changes is the sign of the radical. We don't change the sign of the whole number. Okay? So if someone wrote it like this, the square root of 7 plus 6, the conjugate really is negative square roots of 7 plus 6. So you might want to make that note in your notes, that your conjugate is just changing the sign of the radical. Okay? Because it's in the form of a plus the square root of b. So your square root is the only thing that changes the sign, not the whole number. Just the sign of the radical changes. Okay? So that's that whole second half of multiplying and dividing, stuff like that. So that's where we're going to go from there. Your assignment you'll have here in a second to work on the rest of the hour. Goodbye.